Up until this point, we have seen examples of conservation of momentum in inelastic collisions, and puzzles where an inelastic collision was solved by using information from kinematics. In this video, we will examine more advanced types of collisions in which conservation of energy plays a role. So far, we've seen inelastic collisions, where two objects collide and stick. A collision where two objects bounce, like billiard balls, is called an elastic collision. The formal distinction between an inelastic collision and an elastic one is that in inelastic collisions, momentum is conserved, but some or all of the kinetic energy is lost as work out due to friction, or otherwise turned into heat as the objects stick together. In elastic collisions, both momentum and kinetic energy are conserved. Let's consider this case. A 2 kilogram red object moving at 5 meters per second strikes a 3 kilogram blue object at rest. It bounces off. What are the final velocities of the two objects? First, let's set up conservation of momentum. Plugging in all the information we know, we get this equation, which relates the final velocity of the red block to the final velocity of the blue block. 10I hat equals 2v2 plus 3v3. But we can't solve a single equation with two unknowns, so we also have to turn to conservation of energy. In this case, conservation of energy has to account for the kinetic energies of both the blocks before the collision and the kinetic energies of both the blocks after. Substituting in the information that we know, we get this equation. 50 is equal to 2v2 squared plus 3v3 squared. Now it becomes a matter of solving these two equations simultaneously. One way to do this is to rewrite the momentum equation such that v2 is isolated. We then substitute this expression for v2 into the energy equation. This yields a quadratic equation. We can then solve for v2 using the quadratic formula to get v2 equals 4 or v2 equals 0. 0 was the velocity before the collision, so 4I meters per second is the velocity after the collision. And we can plug this into the conservation of momentum equation from earlier to solve for v1, which is negative 1I meters per second. So this elastic collision was solved by using both conservation of momentum and conservation of energy, finding two different relationships between the final velocities and solving simultaneously. Now, a variant. What if the 2 kilogram object were moving at 5I meters per second as before, but the 3 kilogram object were moving at negative 4I meters per second? How would an elastic collision play out then? As before, we set up conservation of momentum. We expand the terms and substitute the values in. The difference from the previous example is that the initial velocity of the second block, the blue block, is no longer 0. The result is this simplified expression for the final velocities. Negative 2I equals 2 times v2 plus 3 times v3. Now, let's turn to kinetic energy. Again, we will expand and substitute all the values in. When we simplify, we get this equation. 98 equals 2v2 squared plus 3v3 squared. Now, we solve the two equations simultaneously as before. We isolate v2, substitute that into the other equation to yield a quadratic equation, and then solve that quadratic equation. When we do, we end up with v3 is equal to 3.2i meters per second, or v3 equals negative 4i meters per second. -4 was the velocity before the collision, so 3.2i must be the velocity after. And as before, we substitute that back into conservation of momentum, and we get v2 equals -5.8i meters per second. Elastic collisions in 2 dimensions occur when one object, like a billiard ball, hits another and deflects or scatters. If we were to take their velocities after the collision, we could break them into their x and y components. Momentum needs to be conserved in both x and y. Let's say that a 2 kilogram ball moving at 5i hat hits a 3 kilogram ball initially standing still. After the collision, the 2 kilogram ball moves away at 3.95 meters per second at an angle of 60 degrees below the horizontal. What is the velocity of the other ball? We start by breaking the 2 final velocities into their x and y components. We then write the equation for conservation of momentum, first in the x direction. In the x direction, let's substitute what we know. The magnitude and direction of the 3 kilogram ball are unknown, but the rest is known. Now, let's do something similar for the y direction. The same 2 variables are unknown. Here's how we solve these. Divide the equation in y by the equation in x. When you do this, the magnitudes of the velocities cancel. Meanwhile, sine theta divided by cosine theta gives you tangent of theta. And so we see that the tangent of theta is 0.912. Taking the arctangent of both sides, we get that theta is equal to 42.35 degrees. Now substitute this value of theta into either one of the equations that contains v3 after. I've done it for the x direction. Simplifying, we get the final velocity of the 3 kilogram ball as 2.95 meters per second. This concludes our discussion of momentum. In the next episode, we will begin the next chapter, rotation.